If you notice on the front page of this packet of notes, what have I already filled in for you?
Oh, it's the thingamajig.
All the formulas. Flip this paper over. You still have the back of this to write down extra things that you want, just like normal. However, I felt like it would be easiest to have all the formulas in one place. We are not going over all of the formulas today. We're doing the basic ones today, and we will build up and add tools to our toolkit as we learn the different sections. Okay, so if you wanted to go ahead and rip this page off and act like it's a formula chart so you could look at it every time, that's fine, because I did not copy paste the formulas into the notes. We're going to be using the formulas throughout the day.
So we can use this one for the template?
Correct. If you don't want to lose it, keep it attached, but if you're wanting to use it as a formula chart, maybe detach it so you can look at it the whole time. But there you go, you already have them written down in typed handwriting, not bad handwriting. Sorry. Okay, you had your hand up, sorry.
So this section, is chapter 5, is that like a really hard thing?
So chapter 5 is, I like to call it a creative thing. So the reason that I took it off of the internet, like I didn't have you do online homework, is because the online textbook had you solve these problems one particular way. There is more than one correct way for the most part to do a lot of these problems, so I want you to be able to be creative. Basically, what we're going to be doing today is taking other definitions of the trig functions and substituting them in to simplify expressions down. That's the main concept of this entire chapter. But there's a lot of trigonometric identities, as you can see on this front page, that we're going to have to be using. Okay, the first formula we're going to be using today will be called the reciprocal identities. I know that the highlighters are not out because we're in SAT testing mode, so like if you're desperate for highlighters, they're actually all behind my desk. I'll pause for a second. Does anyone want to go grab them? It's really not that necessary. Okay, cool. But the reciprocal identities, I'm going to highlight in pink, which didn't show up very well. But our reciprocal identities basically are the reciprocal definitions of cosecant, secant, and cotangent. We actually already know these. These are the reciprocal functions. What that means, though, is if we ever see cosecant of theta, we can take it out and replace it with 1 over sine of theta. That's its identity or its other name. The second set of identities that we're also pretty familiar with are called the quotient identities. I'm going to highlight this one in blue if you care. The quotient identities, again, are the definitions of tangent and cotangent, being sine over cosine or cosine over sine. The third set of identities we're going to use today, I'm going to explain a little bit more. They're called the Pythagorean identities. They follow the pattern of a squared plus b squared equal to c squared, which is Pythagorean theorem. That's why they're called the Pythagorean identities. However, there are 9 versions of the there are 3 versions of each of these 3 Pythagorean identities, because we can solve this equation or derive this equation for its alternative forms. For example, if I took this first equation right here and I subtracted cosine squared of theta to the other side, we'd have the equation sine squared of theta equal to 1 minus cosine squared of theta, correct? I just subtract it to the other side. That's an additional way we can write this first Pythagorean identity. I subtracted cosine to the other side. So there's 9. If I resolve this to set cosine of theta by itself, that would mean I'm subtracting sine of theta to the other side. This would be 1 minus sine squared of theta. I like to personally see these alternative forms of it, because a lot of times we actually see these alternative forms in problems more than we see the basic derived forms from Pythagorean theorem. If we're doing the same thing for that middle identity, tangent squared of theta plus 1 equal to secant squared of theta, let's subtract 1 from both sides. So that would mean tangent squared of theta would be equal to secant squared of theta minus 1. Do we see how I'm just deriving this for each version? If I set this equal to 1, that means I'm subtracting tangent from both sides. This is the same thing as secant squared of theta minus tangent squared of theta. All 3 of these are identities and allow us to substitute things into problems when we recognize these identities. If I look at the third version, let's isolate the 1, which means we're going to subtract cotangent squared of theta from cosecant squared of theta. Or we isolate the cotangent squared of theta by subtracting 1 from both sides. So these are the 9 versions of the 3 Pythagorean identities. We need to be on the lookout for any of these so that we can substitute them for something simpler. This feels like a lot, but what I want you to remember is that each and every single one of these identities, they're all squared. So if you have some squared stuff, brain might be thinking, okay, Pythagorean identity, and they're all either plus or minus or equal to 1. So if you notice there's a 1 and some stuff squared, you might be using a Pythagorean identity to simplify this down. That's just a good rule of thumb. The last set of identities that we'll touch on today are your even and odd identities. This literally has to do with the fact that 2 of these functions are odd functions and 2 of these functions are even functions. Sorry, 4 are odd, 2 are even. So if we think about it, sine and tangent are odd functions. So that means that if we're doing a negative angle, we can just basically take that negative and stick it on the outside of the sine or cosecant. That same thing happens for tangent, where if you're doing the negative angle, it's just the negative of that operation, that tangent or cotangent. However, cosine and secant are even functions. They fold along the y-axis, which means the left side is equal to the right side. So we basically can take a negative angle and make it equal to the positive angle. See how there's no minus sign in front of these? That's an even and an odd identity. We don't see these necessarily as much. And in fact, I actually don't think there's an example in your notes today with the even odd identity, but there is a few on your homework. So we'll go over one of your homeworks before we're done with the lesson today, just because I realized it's not on there. That's where we're stopping today, these 4 identities. These are what we're going to be looking out for to rewrite and simplify trigonometric expressions. There will be no equal signs today. No. You're not solving anything. Don't add equal signs where there's not equal signs. These are all things I see people do when we do these problems. We are just simplifying these things down. Can I show you what a problem like this looks like? Yeah. Great. You don't have a choice. We're doing it anyways. So a fundamental identity, remember we kind of talked about this. An identity is an equation that is satisfied by every value in the domain of its variable. Basically, you can take these things out and put the identity in and make it simpler. Our goal here is to cancel stuff out, multiply things, factor things, do a whole bunch of algebra with trig functions to simplify these down to one or a simpler expression. So for example, we're going to take sine of theta multiplied by cotangent of theta and simplify it down in 2 steps to where it is just one trig function. So the first thing I'm going to do is I'm going to be like, all right, this cotangent can be rewritten using its quotient identity. What is the quotient identity of cotangent? Cosine over sine, right? Yeah. So, I was going to do that in color. Cosine of theta over sine of theta. Cotangent is cosine over sine. That's due to the quotient identity. Are y'all okay with me using shorthand QI for quotient identity? RI will be reciprocal identity. PI will be Pythagorean identity. Even odd, I'll probably write the words out because that's not too long. Okay. But do we see all I've done? I've taken the definition of cotangent and I've used it. Okay. What do you now notice is on top and bottom of this fraction? There's a sign on top, there's a sign on bottom. That's going to cancel out, which means all I'm left with is cosine of theta due to the fact that I can cancel the signs. And voila, I'm finished. I have it down to one trig function simplified down. When we do these problems, I am expecting that you give me a reason for each step that you take, which is why in these first few problems I've given you like a little chart to fill out. There's a step and then a reason. A step and a reason every time. Let's see another example before we ask any questions. Let's go to this one. A good rule of thumb is to always change things, if you don't know what to do, change things into terms of sines and cosines. So the first thing I'm going to do is look at that first. These are both sines and cosines, yeah? We leave it alone. This second one, though, can I change this into sine or cosine? Yeah, what's its reciprocal identity? 1 over sine. So this is going to be sine squared of theta over cosine of theta, no change. Didn't change anything there. And I'm going to rewrite cosecant as 1 over sine of theta. That is the reciprocal identity.
Wait, what is it, RID?
Reciprocal identity. So it's the heading of the, if you're looking at the formula chart front page, that's the heading of that row. It says reciprocal identity. Is anybody spidey senses going off?
Yeah, they cancel.
What cancels?
Sine.
Okay, question though. This is sine squared.
Ours was one of them.
So one of the signs will cancel and the sign in the bottom will cancel. So here's how I recommend showing your work here. You cancel out the sign in the bottom and you cancel out the 2. Right? Because it's squared, so it's no longer squared. Just cancel that out. So then I'm left with sine of theta over cosine of theta. That's a cancel step. And if I only want this in terms of a single trig function, I need to do something with this entire thing so that it becomes one trig function. Yeah, isn't sine over cosine equal to tangent anyways?
Yeah.
So this is tangent of theta due to the quotient identity. Do you see how we're just switching things around with their identities, moving them in and out to try to cancel stuff down? Yeah. There are a lot of these problems, there are many ways you could start. And sometimes you're getting started, you're doing stuff, and you're like, whoa, I'm doing too much. This is an assignment I highly recommend doing in pencil, and pencil only. Because you will make mistakes, because you'll go down a pathway of trying to solve something and be like, I think I've made this more complicated, let me back up. This is the game we're playing here. Let's see a few more examples together. Okay, for this one, I did just recommend that the best thing to do is to change things into terms of sines and cosines, right? Can I write this as a sine and a cosine?
Yeah.
Yeah, I'm going to use the reciprocal identity here and change this into sines and cosines, which means I'm rewriting it as what? 1 over sine squared of x. So the square goes with you. When you're doing a reciprocal or a quotient identity, the square stays with it. Okay, that's all I've done. I'm going to rewrite down this stuff. Okay. So that was the reciprocal identity. Awesome. Now, I'm tempted to do this because I have a number in front of a set of parentheses. So we distribute into that parentheses. 1 times sine squared of x is 1 over sine squared of x. And then negative cosine squared of x over sine of x, because we would multiply. So that is a distributing step. Interesting.
Why are you distributing?
Why am I distributing?
Yeah.
As opposed to what?
As opposed to using sine squared. Okay.
Oh, the Pythagorean identity?
Yeah.
You could have done that.
Oh, okay.
This is what I mean by there's many ways to solve this. Let's finish this way and then I'll show what you're trying to do. Okay, so from here, I see that I have a whole bunch of things going on. So if I try to make these, let me back up. These are a common denominator, yes?
Yeah.
So if we write them as one fraction, this is 1 minus cosine squared of x over sine squared of x. That's just adding fractions. And then question. Do you know, I didn't give you enough spaces here. You need one more. Do you recognize that that numerator is some stuff squared with a 1? Look at your formula chart. Do you see this anywhere on that formula chart?
That's the
Uh-huh.
That's one of the cotangent ones?
It's the Pythagorean identity, and 1 minus cosine squared of theta on our formula chart is equal to what? Sine squared of theta. So we change ours to sine squared of x because that is the Pythagorean identity. We can totally just switch that out to sine squared of x over sine squared of x. That's the Pythagorean identity. Well, what's sine squared of x over sine squared of x? 1. That's a cancel step. The answer here is 1. Now, don't write this one down, but I just want you to think about this for a second. If we had noticed at the very beginning that this was also that Pythagorean identity, what could we have changed this original parentheses to? Sine squared of x. So then all we're doing is cosecant squared of x times sine squared of x. It would still get us down to 1. No matter what you see first, as long as you are doing correct math and substituting correctly, you will get to the right answer. It would be shorter. I think that's the way I meant for us to do this one, and I think you only need 3 steps, which is why there's only 3 lines. Don't be scared. All right. What do y'all want to do first?
Not the problem. Distribute.
Okay, I hear it. Let's do distributing first. So we do boop and boop. So what is sine times sine? Sine squared of x, and then minus, this would just be cosecant of x times sine of x. So all we've done is distribute. Okay, done. What next? It's a good rule of thumb that, especially if you have no idea what's going on, to change all of the terms that you have into terms of sines and cosines. So let's rewrite cosecant in sine or cosine. What is cosecant? 1 over sine. So I can rewrite that little bitty part as 1 over sine of x. Because that is the what rule? Or what identity? Reciprocal identity. All right, what are our spidey senses telling us? Cancel out. Hooray, cancel, cancel, which means we have sine squared of x minus 1. That is a cancel step. Okay, here's where my spidey senses went. I was like, oh, there's stuff squared and a 1. Is sine squared of x minus 1 on your Pythagorean identity list?
No. Yeah. No. Yes.
I'm hearing yes and I'm hearing no. Is it exactly on the list? Sine squared of x minus 1.
No.
What is on the list?
1 minus.
So if I wanted this to switch, because that's what I see on my list, right? That would mean that this went from being negative to positive, and this went from being positive to negative. What can you do mathematically to change the signs of something? Multiply it by a negative. So we're going to stick a negative in the very front. This step, you're going to have to do a lot, and we're going to call it factor out negative 1. Because technically, if we divide both of those terms by negative 1, they change signs, and then I can bloop switch their spots so it matches what I have on my paper, as long as you put that negative in the very front. But now that we have it in the order we wanted, this is from the Pythagorean identity list, yes? What is 1 minus sine squared of x? So then I have negative cosine squared of x. I'm down to 1 trig function, and I'm done. That is your Pythagorean identity. We're not going to go to the next problems till after lunch because I'm assuming we want a second to digest these.
Yes.
Yes, what's up?
Are you only going to cancel once ever, or are you going to have multiple times where you cancel?
There can be multiple times you cancel. Yes.
Is it just these, or can we find other ways to do it? Is there not a certain way?
There's not a certain way, which is also why I wanted to go on paper, because I want your creativity to take over. The book had one way it wanted you to do it, and it wasn't always the way I chose to do it first, so it made me mad. So we're on paper. I will say, do you see how each and every time I did one thing and gave one reason? Even if you can see 3 steps ahead, I'm requiring you to show me 1 step at a time. That's what I'm wanting. So your homework, you will do one thing at a time and give me a reason each time you do it. That is the problem. The work is the answer. The steps that get you there is the answer. This is essentially an informal proof, air quotes around informal proof. Other questions before we go to lunch? Okay, we'll try a few more after lunch. As we're solving these problems, sometimes we're going to have to use some other algebraic skills to get things to start to cancel. One of those algebraic skills that we're going to maybe need to do is to multiply by the conjugate of the denominator. What does conjugate mean? Do we remember this from college algebra at all?
No.
Conjugate of, especially when we did this when we were dealing with imaginary numbers, was like the negative version of the imaginary part. So instead of a plus bi, it was a minus bi. AKA, take the denominator and multiply the top and bottom by the opposite sign. Meaning, I'm going to take the original problem, sine of theta, over 1 plus cosine of theta, and I'm going to multiply it on the top and bottom by the conjugate of that denominator, 1 minus cosine of theta on top and bottom. The reason we want to do this is because there is no squared terms here. There is nothing that I can change into terms of sines and cosines. I'm kind of at a standstill. But when we do this, which by the way, this step is multiplying by the conjugate, we are going to get the following. We have sine of theta multiplied by 1 minus cosine of theta in parentheses. And we have 1 plus cosine of theta multiplied by 1 minus cosine of theta. Okay. Cool, cool, cool. We're going to leave the numerator as it is. And we're going to focus on this denominator for a second. You see how we have a binomial times a binomial? We're going to have to FOIL this. Which means that not changing the top at all. This, that's the wrong function. Cosine. This becomes 1 times 1, which is 1. 1 times negative cosine of theta, which is negative cosine theta. Cosine of theta times 1, which is cosine of theta. And then cosine of theta times negative cosine of theta, which is negative cosine squared of theta. What's up, Joseph? No, ask for a question.
No, I saw something. I never.
Okay. For those of you like, what is Miss Quigley multiplying together? I'm not drawing the arrows because it would get really confusing on here, but I'm doing this. Distribute, distribute. That's what I mean by foiling. It's double distributing. Let me turn this TV down. Really loud. Is anybody's spidey senses going off about this problem in the denominator?
Yeah.
We can cancel this stuff in the middle, right?
Yeah.
So the cosine and the negative cosine cancel each other out. And I'm left with sine of theta times 1 minus cosine of theta over 1 minus cosine squared of theta. If you notice, there is a shortcut we could have taken here. Instead of doing the entire FOIL step, if you notice that these are the same terms, one of them being positive, one of them being negative, which we did on purpose, this is the difference of two squares. First thing squared minus second thing squared. That will always happen when you have the difference of two squares. So if you see that, you can take that shortcut. If you don't trust yourself to do that shortcut right, just FOIL it. It's not that much harder. Okay. Huh? FOIL will always work. Is anybody's spidey senses going off about something else here? I heard a lot of things. Here's one of the things I heard. Something cancels. Not yet. Notice that this is an entire parentheses that says 1 minus cosine of theta. This parentheses would say 1 minus cosine squared of theta. Are those the same things? No, so we can't cancel anything out. The cosines won't cancel because there's a binomial on the bottom. We don't do canceling that way. But maybe your spidey senses should be paying attention to this denominator again.
Oh, yeah.
Oh, yeah. Yeah, this is one of your Pythagorean identities. What is 1 minus cosine squared of theta equal to? Sine squared of theta. So I'm going to rewrite that part down. So I just, again, this numerator has come with me this whole problem. And this becomes sine squared of theta. That is your Pythagorean identity. Now what cancels?
Sines.
The sines. One of the sines in the denominator and the sign in the numerator will cancel out. So then I have 1 minus cosine of theta over sine of theta. This was a cancel step.
And it should be 1.
Oh, thank you. Yes.
I'm a little confused.
Yeah, sure.
How come we can't cancel that out, but we cancel that out?
That's a great question. It all has to do with the fact that the first one that I've highlighted in green is a binomial. I mean, there's two terms. There's a something and then a plus or a minus sign and then something else. We can't cancel the way you want to when you have a binomial. When you're canceling, it's because it's a monomial. This is a monomial, one term. No pluses or minuses. One term, monomial. Is that a good explanation for you? Okay. Now, only because I know where this problem wants you to end, this problem would have given you the instructions. Simplify this to where it is two terms with no fractions showing. So we need to get rid of the fractions in this problem. So what I can do with a monomial denominator is I can split that denominator to both pieces in the numerator. This is an unmathematical term for what's happening, but I've always called it the split. You can only do the split when there's a monomial in the bottom. You can only do the split when there's a monomial in the bottom. If there's a binomial in the bottom, it's not splitting, only when there's a monomial in the bottom. But now that we have this as two terms, which is what it asked for, two terms, we need to get rid of the fractions. If we get rid of the fractions, that means I'm looking at this for this to go away. How can I get rid of the 1 over sine of theta? That's cosecant of theta. So we can use the reciprocal identity to do cosecant. And just because we're running out of space, I'll allow you to do two things at once. This one. This is the last step. This is cotangent of theta. And that's the quotient identity. And that's it. So part of the game here is making sure, and I didn't write the instructions on these notes, but making sure you're following what the instructions want. This one would have said, I want two terms with no quotients showing, no fractions. So we had to keep reducing this down until we had two terms, no fractions. So we're using a lot of algebra with trig functions. It's so cool.
No, it's not.
It really is.
My brain hurts.
It's like a puzzle.
I won't do that.
Let's go to the next example, and it has a mathematical hint for you there. It wants us to simplify this down, and if this was on your homework, it would say to a single term with no coefficient or no quotients showing. So since these are two separate fractions, the only way I'm going to combine them into one term, one fraction, that eventually I have to get rid of, is to find a common denominator. What would be the common denominator if I took this and multiplied it by this? 1 minus sine of theta, 1 plus sine of theta with parentheses. So look, this is what I'm doing. This is a long step. We're going to have this denominator be 1 minus sine of theta, 1 plus sine of theta. But we have to do this to both fractions. So I'm setting myself up to make it a common denominator. What's up?
Isn't this a difference of squares? Can't we just put 1 minus sine of theta at the bottom?
That's fine as long as you tell me that that is the step that you also did, because we're going to do that in just 1 second. But for our notes, I'm making sure we see why this happened. But if you already see it, go for it. Okay, in this first fraction, it already has the 1 minus sine of theta. So what did I have to multiply here to give it the same denominator? It already has 1 minus sine of theta. 1 plus sine of theta. What you multiply in the bottom, you have to multiply in the top. For that second parentheses, it already had 1 plus sine of theta. So what am I multiplying? 1 minus sine of theta. Why do I have these ones right here, by the way? Because they were already in the numerator. If there's a number there like 2 or there's a function like sine, you keep that there. Whoa. All right. What did we do there? That step was called finding a common denominator. Not quite yet. Well, we don't want to cancel them out because we just added them there. We just put them there. So I'm going to do a couple things at once. I'm going to write these as one fraction, 1 minus sine of theta, 1 plus sine of theta. And I'll allow you to do this distribution and add these fractions at the same time just to save space. 1 times 1 is 1. 1 times sine of theta is sine of theta. 1 times 1 is 1. 1 times negative sine of theta is negative sine of theta. So what did we do here? We added the fractions and did some distribution. Do you notice anything about that numerator? What cancels out? The sign. We have a positive sign and we have a negative sign. Those are going to cancel, which means my numerator becomes what? 2. Now, we will also, this is combine like terms or cancel. I guess I've been using the word cancel. Let me use the word cancel. So we're going to cancel. And we'll go ahead and FOIL that denominator, which again, if you see the difference of 2 squares, take it. If you don't, here's what we're doing. 1 times 1 is 1. 1 times sine is plus sine of theta. Negative sine of theta times 1 is negative sine of theta. And negative sine of theta times sine of theta is negative sine squared of theta.
This is what my square did. Sine squared.
So the signs in the center will cancel out, yes. This becomes 2 over 1 minus sine squared of theta. That was a cancel step. Or if you had taken the difference of 2 squares at the beginning, as long as you told me that's what you did, you've given me a reason for your step. Whose spidey senses are going off? Maybe particularly about this. What is 1 minus sine squared of theta? Cosine squared of theta. And then since the problem told me that I want to not have any fractions, I got to get rid of that cosine squared of theta that's in the denominator. How do I get rid of it? Okay, look at your formula list. Is there any formula where cosine is in the bottom? I think I heard somebody say it. Secant. Secant is defined to be 1 over cosine, which means if you see cosine in the denominator, you can take it out of the denominator if you make it a secant, because that's the definition of secant. So this is just secant squared of theta due to my reciprocal identity. And since I'm done, I have no more fractions and I have one term. That's how I know I'm finished.
Yay.
There's many ways to do these problems. You have to let your creative brain take over, because usually when students ask me how to do a problem, I have to read through their work first, because you might have solved it differently than me. Doesn't mean it's wrong, just means it's different. We're going to do 2 more examples just to give you more ideas of something you can do. So another thing we can do if nothing cancels out is we can factor both the numerator and the denominator. I 1000% know that that numerator can change to sine squared of v, but it actually doesn't help us with this problem. So if you were doing this problem on your homework and you tried that, then you would kind of be stuck elsewhere. So we're going to leave that for a second. What we're going to do is we're going to factor both the numerator and the denominator. Do you notice that the top is the difference of 2 things that are perfect squares?
Yeah.
Which means that this would factor to 1 minus cosine of v, 1 plus cosine of v. I'm going to put factor and then difference of 2 squares, if that's okay with everybody. Now, what about the denominator? Can that factor difference of 2 squares?
Yes. Well,
It's 2 things, yes. Are they subtracting? No. Okay, so it's not difference of 2 squares. But what do they both have in common, both terms?
sine.
They both have a sine, so we can factor out the GCF, which is sine. So we factored by a difference of 2 squares in the numerator and our GCF in the denominator. Now you can think of the denominator, I know I said this earlier, of it being a monomial. We technically have a monomial here if you're thinking about this parentheses multiplied by here. Meaning, don't do this because you'll be mad at yourself. If I covered this part up and just put like the number 5, 5 sine of v is a monomial, 1 term, no plus or minus, correct? Which means if I see the same thing on top and bottom here, I can cancel them. Do you see that that entire parentheses, 1 plus cosine of v, is on top and bottom?
Yeah.
With no parentheses on the top or on the bottom separating them? That means I can cancel those. So this becomes 1 minus cosine of v over sine of v. This feels like an apt time to say, look at your work and make sure you're writing the variable. In the first problem, we were using thetas. Second problem, we were using theta. In this problem, we're using v. Anytime you write sine, cosine, or tangent, or its reciprocals, a letter has to follow it. Make sure you use the letter that they're using. Okay, cool. The instructions on this one would have said, write this as 2 terms with no quotients showing. So I'm going to split this just like I did the question before this, I'm splitting with the monomial denominator, basically undoing addition of fractions. Again, not a mathematical term, we're calling that a split. This should sound familiar to you, because what is 1 over sine? Cosecant. So we can use that reciprocal identity to change this one to cosecant of v. And then again, we'll just do this all in one step because I can see it. What does this change to? Cotangent of v. So this one becomes cotangent of v due to the reciprocal identity and the quotient identity. And since I have two terms with no fraction showing, I'm done. Do we kind of see how the game works a little bit? The cool thing, which is also unfortunate, is that there's not like steps I can tell you to do every time, because every problem is different and can be solved differently. A good rule of thumb is when you're stuck and don't know what to do, you can always change things into terms of sines and cosines and go from there, which is what we're going to end up having to do here. Because I already solved this one 3 different ways on my paper, what do you guys see first? Do you see anything? I know the hint says to write in terms of sine and cosine and then simplify, but do you see something else? The numerator, we can use a Pythagorean identity, correct? This one I can rewrite as cosecant squared of theta. Awesome. Do you see anything else? 1 minus cosecant squared of theta. Is that also on your list somewhere?
Yes,
Cotangent squared.
That one's equal to cotangent squared of theta. So with 2 Pythagorean identities, I can immediately change this to already starting to look a little bit simpler. Cosecant squared of theta over cotangent squared of theta. That's a Pythagorean identity times 2. We did it twice. Awesome, great, amazing, except that I don't know what to do now. A good rule of thumb when we don't know what to do is take the hint that they gave you. Write everything in terms of sines and cosines. How do I rewrite cosecant in terms of sine and cosine? It is 1 over sine. So cosecant squared of theta is 1 over sine squared of theta. How about cotangent? Cosine over sine. So that was the reciprocal identity and a quotient identity. Ugh. You got fractions and fractions. I don't love that.
Oh, can we cancel?
We can keep, change, flip. Remember, when you are dividing fractions, you keep the first fraction that's in the numerator, you change the big divide to a multiply, and you flip the second fraction. Keep, change, flip. I almost wrote KFC. I promise I ate. Always. Always hungry. What are your spidey senses saying?
Cancel.
Cancel. What cancels?
Sines.
The sine squared of theta on the numerator and denominator, which means I'm only left with 1 over cosine squared of theta. That's a cancel step. We are 1 step away from being done. What is that last step?
Secant.
Yeah, 1 over cosine is the identity of secant, which means using that reciprocal identity, I can take this back to secant squared of theta. And that's it. Okay. So that's it for today. We're only working with those first 4 identities. And if you're like, Ms. Quigley, we didn't even touch the even odd identities. I know, there was not an example in your notes, so we're going to do one of the examples that's on your homework together that has that. So what I want you to do, because I want you to show me every step, I've given you the quad paper. We're going to use the quad paper as quad paper. Like actually let it tell you how to write, how big to write. Use the quad paper correctly. And we're going to do example number 10 on your homework. You can do them out of order. So on your blank piece of paper, make that number 10. simplify the expression 1 plus cosecant of negative theta over cosecant of negative theta to two terms such that no quotients appear and all functions are of theta only. Show and label all steps of your work. So our goal is to have two terms, no quotients left. But I also need to make sure I get rid of the negative thetas from this question. So we look at the even and odd identities. What is the even odd identity for cosecant of negative theta say that it's equal to? Negative cosecant of theta. So what I'm going to do is I'm going to change this to negative cosecant of theta, which means I can also change the denominator to negative cosecant of theta. That is the even odd identity. See how I'm using the boxes to actually tell me what size letters to write? Sometimes y'all be using this quad paper and writing sideways on it. It drives me bananas. It tells you how big to write. Okay, great. Since I have a monomial in the denominator, I can do that split step where I'm splitting it to both terms in the numerator. So this becomes 1 over negative cosecant of theta minus cosecant of theta over negative cosecant of theta. That's a split step. Anybody's spidey senses going off?
Yeah.
Yeah, what's happening here? What? Oh, you mean that second one cancel? Okay, so if these cancel, pow pow. What am I left with over there?
1 over negative cosecant.
The whole thing goes away?
Oh, no.
When you have like 5 over 5, what is 5 over 5?
1.
So what is cosecant over cosecant?
No,
1.
1.
So I have a minus minus 1. Why did I put minus minus? Because of this negative right here. So really, ew, gross. How could I rewrite that?
Positive.
As a plus. Minus and minus really means plus. Anything else we can do here? I need to get rid of fractions. It says no quotients.
You can change the cosecant.
Yeah, 1 over cosecant. What can that change to? Sine. So this is negative sine plus 1. I forgot to write a reason. This is cancel. And then this is your reciprocal identity. Look how nice and neat we wrote on our boxes, boxed paper.
If you want to call it nice.
On all of the problems for 1 to 15, which the first 4 are basic definitions with the even and odd, I do want you to show me a reason for each step. I highly recommend doing these sorts of problems in pencil because there is a chance you start to work it and realize, I think I'm making this more complicated as opposed to less complicated. So I erase, I try again. Yes?
Sure.
Sure, that's the spirit.
Yay.